This is the first topic in section 5.2 in our text, and it's about counting factors. So how many factors, given a number n, okay, how many factors does that number have? So just a little bit of review. For whole numbers a and b, a is a factor of b if b equals a times k for some whole number k. So let's sort of think about what that means, okay, in terms of like an 8, for example. Okay, this says that 8 is a factor of 48, okay, and that's also written like this, written as 8 divides 48, okay, that's the way 8 is a factor of 48, and 8, sort of horizontal line, divides 48, mean one and the same thing. Why is that true? Because there's a whole number 6, so this serves as our k, such that 48 equals 8 times 6. So if 8 times something equals 48, then 8 is a factor of 48. In this section, the question is, how many factors does a number have? Many numbers are easy to factor, these things that you've been doing for many years yourself. And you just sort of say, okay, this is how many I've got. So, for example, if your number is 6, we know that the factors of 6 are 1, 2, 3, and 6. These are numbers that divide into 6 evenly. Factors of 8, 1, 2, 4, and 8. Okay, and this sort of leads to something that's a little bit of an aside, but I think it's always nice to talk about things like this. Numbers can be classified by the number of, or by their proper factors, okay? And a proper factor, that's a tongue twister, a proper factor is a factor that's less than the number itself. So the number 6 has 3 proper factors, 1, 2, and 3. 6 is the number. The number 8 has 3 proper factors, 1, 2, and 8. So the numbers, if you look at their proper factors, can be categorized into 3 categories. Numbers could be abundant, deficient, or perfect. I like that. A perfect number. An abundant number is one where the sum of the proper factors is greater than the number itself. A deficient number is a number where the sum of the proper factors is less than the number itself. 8 is an example of a deficient number because 1 plus 2 plus 4, those are the proper factors of 8, is less than the number itself. So 8 is a deficient number. And lastly, there are perfect numbers. For a perfect number, the sum of the proper factors equals the number itself. 6 is an example of a perfect number because its proper factors, 1 plus 2 plus 3, equals the number itself, which is 6. So 6 is a perfect number, 8 is called a deficient number, and in abundant numbers, the sum of the proper factors is greater than the number. That's sort of an aside. Let's focus on counting factors. We already know that the number of factors that 6 has 4 of them, 1, 2, 3, and 6. So I'm going to start off with this simple example and sort of identify strategies, general strategies we can use for any number. The first strategy is called the prime factorization table strategy. So we'll call it the table strategy in this video. Both strategies start off by finding the prime factorization of the number. So the prime factorization of 6, which you can use a factor tree if you like, or just doing a list, it's 6 equals 2 times 3. Those are the 2 prime factors of 6. And I'm going to write those with their exponents. 2 is 2 to the first. 3 is 3 to the first. So they have exponents 1 each. For the table, then, what you do is you create a table of possible combinations. As I was writing that, I thought that sounded sort of like, Harry Potter, the mirror of Aristotle, or the table of all possible combinations. All you do is you say, okay, well, what are the possibilities for 2? I could have 2 to the 0 means 2 is not there, or I could have 2 to the first. So these are the possible 2's that can be included in a factor. You do the same thing for 3. 3 could be 3 to the 0, 3 is not there, or 3 to the first. So these are the possibility for 3's. And then what you do is you just form all possible combinations. 2 to the 0 times 3 to the 0 is 1 times 1 is 1. So that's a factor of 6. 3 to the 0 times 2 to the first, 1 times 2 is 2. So you see what I'm doing is I'm just multiplying. This is 1 times 1. 1 times 2. Just sort of multiplying across. So 1 times 2 equals 2. This would be 3 times 1. 3 to the first times 2 to the 0. That equals 3. And 3 to the first times 2 to the first, which is 3 times 2, equals 6. So those are the 4 factors. A nice sort of byproduct of the table strategy is you actually come up with the factors themselves. 1, 2, 3, and 6. Let's do this for a little more complicated number, 44. What are the factors of 44? The prime factors of 44, the prime factorization, I should say, is 44 is 4 times 11. So that's 4, or 2 squared, times 11 to the first. Remember, write your exponents in these. All the possibilities for 2. You could have 2 to the 0, meaning 2 is not there, 2 to the first, or 2 to the second. Those are the possible 2's that could be included in a factor. 11 could have 11 to the 0, meaning 11 is not in your factor, or 11 to the first. So these are the possibilities for 11. Then just multiply. 1 times 1 gives me a factor of 1. 1 times 2 is a 2. 1 times 4 is a 4. You see what I'm doing? Just multiplying. 11 times 1 gives me a factor of 11. 11 times 2 gives me 22. And 11 times 4 gives me 44. Those are all the possibilities. So there, not only are there 6 factors, but the table approach actually gives you all 6. Wonderful, isn't it? That's probably what you're thinking to yourself. Well, here's where the table gets a little complex and is maybe not as useful. What if I said, as I might do, what are the possible factors of 36,000? The first thing you should do for that is, I'll change my color for this. I'll go to red pen. Is say, what are the factors of 36,000? Using a factor tree, I came up with 2 to the 5th times 3 squared times 5 to the 3rd. Using the factor tree, that's the prime factorization of 36,000. Just as I did with the smaller numbers, I could say, what are the possibilities of 2? These are the possible 2's. You could have 2 to the 0, 2 to the first, or 2 to the second. All these are numbers that could be part of a factor. 2 cubed, 2 to the 4th, or 2 to the 5th. For the 3's, you could have 3 to the 0, 1, or 2, but then you say, okay, well, where do I go? I need another column or something. Actually, if I wanted to do this, I could draw it. I could say, well, I could create a cube, if you will, and these are the 5's going out this direction. But then what if I had 4 of them? Where do I go there? Well, that's the problem with the table. So I just have a conjecture. I was thinking about this, looking at the strategy. 2 has a power, an exponent of 5. And how many levels do you have of that? 1, 2, 3, 4, 5, 6. There's 6 levels. Exponent 5, 6 levels. For 3 has an exponent of 2. And how many levels do you have? 3. 3 to the 0, 3 to the first, or 3 to the second. So it looks like it. Here's my conjecture. If the prime factorization contains p, the prime factor raised to the n, there are n plus 1 possible powers of that prime as factors. In other words, the number of 2's would be 1 more than that exponent. The number of 3's would be 1 more than that exponent. Turns out that this actually works. I wouldn't be teaching otherwise if it didn't work. So let's look at the number for 36,000. 36,000. Again, I'd hate to come up with all these. There's a lot of them. 36,000 has, well, looking at the exponent, 2 to the 5th contributes. The exponent is 5. So 5 plus 1, 6 possible powers of 2 in a factor. 3 squared, the exponent of 2. 2 plus 1 is 3 possible powers of 3. 5 has an exponent of 3, so 3 plus 1, 4 possible powers of 5. And then what you do is you use, as you may have learned in some of your other classes, the multiplication principle. There's 6 different possible powers of 2. From each of those, you'd have 3 different powers of 3. From each of those, you'd have 4 different powers of 4. So the 6 powers of 2 times the 3 powers of 3 times the 4 powers of 4, or excuse me, of 5, that gives you a total of 36 factors of 36,000. Excuse me, 72 factors of 36,000. And again, I'm glad I don't have to list them all out. So let's look at that last strategy. And this is a strategy that you use the exponents alone rather than the table. So we'll call that the prime factorization exponent strategy. All right. Oh, sorry. There you go. So here it is in general. In blue, if your number is prime 1 raised to the n1, prime 2 raised to the n2, and I don't know how, it doesn't matter how many primes you've got, prime k raised to the nk, then there would be n1 plus 1 times n2 plus 1 times as many as you have, nk plus 1 distinct factors. So let's just check that this works using what we already know. You know, for example, we know that 6 has 4 distinct factors. We actually found them all using the table. Using the exponent strategy, the exponent is 1, would have 1 plus 1, or 2 possibilities for 2. 3 raised to the first would have 1 plus 1 is 2 possible values for 3. 1 plus 1 times 1 plus 1, 2 times 2. There are 4 distinct factors of 6. That seems to work. Let's check it out for 44. Remember, in 44, using the table, we said it has 6 distinct factors. Well, let's check that out using the exponents. 2, the exponent of 2 on the 2. So 2 plus 1, remember, add 1 to your exponent. 11 has an exponent of 1, so 1 plus 1, add 1 to your exponent. 2 plus 1, which is 3, times 1 plus 1, which is 2. That equals 3 times 2, 6 distinct factors. Check plus means I think we do have it. This is how you use exponents to count the number of factors.